Okay, give that one a shot. Without the distraction of screens. And if you didn't hear that, you're really distracted. Tell your neighbor.
All of it's today.
Okay, correct answer is? Okay. Get it with that? You only get it when you go from high to low. Good with that? Okay. Proof of concept.
Yeah, press and troughs and things. Yeah, go ahead.
Do you have a better laser?
Which kind?
I don't. Anything that can be seen. Mine's like.
Yeah.
Sorry.
No, we're good. Were they not back here?
Oh, I didn't look. I just had one that's.
Yeah.
I have to beat
Yeah, yeah.
a lot.
I got new ones.
Sometimes it takes a while to warm. That's okay. Sorry. Ooh.
There you go, baby.
Nice. Thank you. Thank you.
All right. Okay. Sound and standing waves.
All right. We just got upgraded. I don't have to beat this one. Don't know what that does though. Whoa! That is not what I need. Wow, that's bright. Woo! That's an upgrade. All right. So, I'll do it for. Okay. Do not shine that in your eye. All right. That is hardcore. All right. So this is the refracted ray that I care about. So here, getting closer and closer, you can see on the wall, right there is a critical angle. Does that make sense? Okay. Now, notice, so doing a critical angle here, you'll never get a critical angle. because it always bends towards the normal line. Does that make sense? Okay. So here, watch what happens when you go, okay, so I'm looking at this ray right here. Watch what happens to the brightness when I exceed the critical angle. So right there, see how the brightness gets brighter? That's because the part that gets, so this beam is split. One's getting out, the other is being reflected. But when it's totally internally reflected, none of it's getting out. All of it's totally internally reflected. And so it's like 100%. It's not being split. Does that make sense? Okay. So going in like this, you're never going to get, that is so impressive. You're never going to get total internal reflection. You're going from low to high. It only happens when going from high to low. Okay. So this guy is what we're focusing on. And here, that would be, that is a lot going on there. That's so intense. Right there, total internal reflection. So do you see how that reflected ray gets brighter after I surpass total internal reflection? Good? Okay. That is like dangerous. All right. Nope. All right. So critical angle between glass and water. To calculate that, notice I do not need to tell you which one is N1 and which one is N2 because it has to go from high to low. So on the homework on test, when I say calculate the critical angle, it can't, you have to go from a high to low. So you're using Snell's law. Okay. So you're going from a high, and theta 1, this is our critical angle, that's what we're looking for, equals N2 sine, and what is theta 2? 90 degrees. So we're going, is always measured from the normal line. Good with that? So like here at the critical angle, refractor ray is going like that. We're measuring that angle there. That's theta 2. Okay. So sine of 90 is what? 1. Okay. So that takes care of that guy. So I've got 1.33 divided by 1.52. Check this out. This is a pretty user-friendly equation. Let's say you mess this up. Let's say you flip-flop those. If you had 1.5 or 1.3, you're going to get something more than 1. Does that make sense? If you take the inverse sign of something more than 1, what is your calculator going to tell you? Error. Sign has to be less than 1 or less than 1, right? Okay. So if you get error on your calculator, you know you flipped those two. Okay. Plug this into your calculator, and you find that to be 60 something. Where you got that? 61? 61 degrees. It's your critical angle. Good with that? Okay. So this is showing what I just demonstrated in the fish tank. Okay. Thumbs up when you have a guess. Have a conversation. Correct answer is? Okay. So here is, this is your critical angle, causing your refractor ray to go parallel to the surface, perpendicular to the normal line. So anything that exceeds that is greater than the red angle is going to have total internal reflection. Your blue and your purple are going to totally internal reflect. Okay, good with that? Okay. Hey, you're good. Have a conversation. And tell them why you think so. Correct answer is? Correct answer is A. Let me talk you through it. Let's say the critical angle was green. Red, blue, and purple would all experience total internal reflection. Yellow would not. If the critical angle was blue, the only thing that would experience total internal reflection in this diagram would be the purple one. Everything else would not experience total internal reflection. Good with that? Okay. So when the critical angle is small, you get a better, higher chance of total internal reflecting. Thumbs up when you have an answer. Have a conversation. Correct answer is okay. Where you get the greatest contrast, the greatest difference in indices of refraction, you get the greatest change in speed. Therefore, you're going to get the greatest bending. Here, this bent a lot. That only happens when you have a really big change in the indices of refraction, a really big change in speed. As you go from the wheelchairs going from the sand onto the sidewalk. Does that make sense? Okay, so D is going to be the answer. This is a difference of 0.9. This is a difference of 0.5. This is a difference of 0.2. This is a difference of 0.3. Good with that? Okay, so does everybody see that diamond has a crazy huge index of refraction? This is one of the characteristics that makes diamonds so cool looking. So we've worked on gem cutting for centuries, trial and error. If a gem is cut correctly, it allows light to come in on all sides, but light that's coming in from the side and the back experiences total internal reflection. And all the light goes in, is made so it only gets out coming out of the top. So if you looked at an engagement ring, the diamond is usually elevated and the backside is exposed, allowing light to get in. But the brilliance is the fact that the light's coming, it's only allowed to come out the top of it. The backside looks pretty dull. The top is like, whoa. Does that make sense? Okay. Another application of something that has a high index of refraction is fiber optic cable. So this, I'm really curious with this strong laser what this is going to do. So this stuff, you're never going to see this outside of a physics class. This is just a chunk of fiber optic plastic built just for demonstration purposes. And you do this so you don't blind. Let's see how blinding this is. That is pretty blinding. Woo! Okay. Don't worry about the end here. All right. So notice how it's bouncing around inside. Okay. It's experiencing total internal reflection. It's acting like a pipe for light. Good with that? That is some intense green light right there. With that. Okay, so usually you will find these in smaller versions. So this Christmas tree has several bundles or a bundle of fiber optic cable here, and that comes out the top. And so what this is doing the same thing I just demonstrated with that big one, the small one. It's acting as a pipe for light, and it doesn't get out until it gets to the end. It gets really intense. Does that make sense? This is just the end, like all I'm doing is doing that. Okay. But what looks cool, you see what, does that make sense what I'm doing here? Cool? Okay. Now, more practical application of this. Ooh, it's fiber optic cable. So around these parts, Metronet and Wintech are the two fiber optic installers providers. Okay. So Wintech is out by my house, so I went out and talked to the technician installing it. Crazy what you get when you're like, I'm a physics teacher at Harrison. I'm like, no. So we geeked out for a little bit. So he was telling me about this stuff. So the little strands here, I'll pass this around. Little strands are the fiber optic cables. These side white pieces are just fiberglass strands to give it strength. There's a copper wire in case it gets struck by lightning as a grounding. Okay, so information is binary, like digital information binary, ones and zeros. You can represent binary with a lot of different patterns. Prior to this, it was alternating current back and forth. Okay, fiber optic cable light can be turned on and off. That on and off pattern sends information. He said one of these little strands is enough, is big enough to provide internet capabilities for 20 households. Okay, which is crazy. And how much resistance is there for fiber optic, like for light, versus like alternating current? There's resistance there, right? This is just light, so it's like crazy efficient. It's just really expensive to like manufacture and install, but it's a worthwhile investment. That's why it's all going in all over the place. That makes sense? Okay. All right. So if you were under the water, remember talking about the spear, like what does the fish see? Okay. So light's coming in, refracts, comes in, refracts, and you think you see the spear up here. If you're under the water with goggles, this is what you see when you're here. The girl is way up here. This stuff is the sand that's experiencing total internal reflection and goes into your eye. The surface of the water acts like a mirror. Okay. So here's some. So try this summer when you're in the pool. Some goggles and look up. So, like here's the outside the pool, but this is acting like a mirror. This is my favorite picture. Hotel swimming pool. This is obviously the edge of the water. The banister jumps from here to here. Does that make sense? Okay, and it's just acting like a mirror here until this point here. That crazy? All right. Um, all right. So if light there it is. All right. Show me with your arm the normal line. Where's the normal line? As it goes from air into glass, is it going to bend away or towards the normal line? So here's no refraction. This is how I'd recommend you drawing this. Okay. No refraction, bends towards the normal line. You all right with that? Okay. Show me the normal line for that interaction, that surface boundary layer. Is it going to bend away or towards the normal line? Going from glass to air. Here's no refraction. It's going to bend away from the normal line. You good with that? Okay. If your eyeball is here and you're looking at whatever produced that ray, you think you see the object right here. So that was a star. See the star there. Good with that? If these surfaces are parallel, then this ray and this ray are going to be parallel. Okay. How much this is offset is dependent upon the thickness of the glass. So this is you looking through a window. Okay. The thickness of the glass and the angle at which you're looking. If you're looking straight on, you'll be able to see it where it is. But if you're looking at an angle, it gets distorted. It gets shifted. I don't know if you can recall that in your experience of looking through windows. Or maybe something you've paid more attention to is when you're in the doctor's office, the reception area, and the aquarium, you can make the fish look in two different spots if you look at it at a really sharp angle. Like, hey, look at that, the 2 feet. Ah. Good with that? Okay. So that's how that happens. Okay. So my recommendation for this question would be to do what we just did with the rectangle prism. Have a conversation. Tell them why you think so. Work on it together. It's a multiple step problem. Correct answer is, well, let's find out together. Show me with your arm the normal line for this one. Perpendicular to the surface. Okay. Is it going to bend away or towards the normal line? Towards the normal line. So here's no refraction. Towards the normal line. So now we're like C or D is our options, right? Second surface. Show me the normal line. Perpendicular to your surface. Is it going to bend away or towards the normal line? Away from the normal line. Does that make sense? Correct answer is D. Okay. The reason it did not go parallel was because the surfaces on the triangle were not parallel. These were parallel. This surface and this surface were parallel. So this ray ended up being parallel. This were not. Good with that? Okay. So here we deviate a lot from the path that we had before. With this big change in direction, this sets the stage for dispersion. We're able to have white light separated out into its colors because different wavelengths have different speeds through this material. Okay, the short wavelength interacts a whole lot more with the atoms, the molecules of this prism, and so it takes longer to get through there. Versus red, it has a longer wavelength, and so it's able to get through with less interference, so to say, and so it's not slowed down as much, and that is what causes white light to be separated. Good? All right, you know that. So where do we find that in nature? Rainbows. Okay, so here's how a rainbow occurs. And you're like, okay, I need sunlight, I need raindrops, and you need your eye. Okay, so sunlight comes in, our raindrop is acting like our prism. When it goes from air to water, it refracts just a little bit. Okay, and then when it goes, so here at this interaction, most of the light actually gets out. Some of it's reflected back in. Okay. Um, but this is the part that makes the rainbow. This part that's reflected back in when it goes from from water back into air, it refracts again. And that's enough to separate that white out just a little bit. Okay. Um, and so here's your dispersion. Um, if you look at this is like either a glass ball or a raindrop. I don't know. Also, I think it's probably glass. But we're shining the laser light through. Most of this gets out here. Only a small fraction is reflected back in. This is the stuff that makes the rainbow. That's why it takes a bright sun to see to produce a rainbow. It doesn't always happen. It's only when you get a bright sunshine after a rainstorm. Okay. Notice how red's on top. Sorry, red is on bottom, but the purple's on top. But if you think about it, what color's on top of rainbow? Red. Weird. That's because all raindrops are producing this rainbow. But the rainbow that you see, or the color that you see, is only from the raindrop that's able to shoot that color into your eyes. So this raindrop is shooting red into your eyes. It's shooting purple over your head. This raindrop is shooting purple into your eye and shooting red at your belly button. Can't see that. It's only what's shooting into your eye. Okay? So if you're ever like, oh man, there's going to be a rainbow, where do you look? Always turn your back to the sun. Face away from the sun. Does that make sense? Okay. And when is it going to occur? What time of day? It's when the sun is near the horizon. Because you're always looking back to the sun. It's going to be that way. Okay. When it's at noon, the only time you're going to see a rainbow is down here, and that's going to be like in a sprinkler and a hose. Does that make sense? Okay. So here, there's a whole bunch of raindrops. These are shooting red light into your eye. Okay. And these are shooting purple. It's actually a cone. Okay. As you take a step closer, you're still seeing a rainbow, but it's from different raindrops. So you're never going to get to the end of the rainbow because it's always moving. Suckers. Does that make sense? And the leprechauns have another secret. It's a complete circle, like the end of a rainbow. It's a circle. Okay. Does that make sense? And the earth just gets in the way because it's a cone. You're looking into a cone. Okay. And for funsies, double rainbow occurs because it's even more rare because light bounces twice in the raindrop, so it's even less intense. So it takes a really bright sun. But notice the color of the order of the colors on the secondary rainbow. See how it's backwards? That's because it bounces twice inside before coming out. That cool? Sometimes in the wintertime, you'll see these smeared rainbows. These are called sundogs. It works like in principle in the same way, but the geometry is different. So these are actually looking towards the sun to make that rainbow. Good with that? No homework this weekend. Well, I mean, you got a project, but there you go.